We're going to start off with looking at HVAC systems and the subsystems that make up an HVAC system. They include the cooling system, the air distribution system, and the refrigeration system itself. We talked a little bit about the refrigeration system down there. We're going to tie that together. We're also going to talk about some theories, some heat and principles of heat and temperature, some laws of thermodynamics, which is important for you to understand, and some refrigeration theory, vaporization, condensation, some of which we've already talked about, and some basic refrigeration cycles and factors that are going to affect heat transfer in our system. It's all about the heat transfer. One of the laws of thermodynamics, there's a few of them now, but two of them that you've already been exposed to. What are they? Give me one. Yeah, laws that affect heat transfer. You know.
Like a law.
A rule then.
Surface area?
Well, surface area will have an effect, but you remember we talked. Pardon me? Temperature difference? Yeah, remember that in order for heat to transfer, there has to be a temperature difference. And remember, when we talk about temperature, we're talking about the intensity of the heat. There has to be a difference between two components in order for the heat energy to get transferred. And the greater the difference in temperature, the faster the rate of heat transfer. So those are two rules that we're concerned about. It's important for you to keep in mind, because if we want to get rid of heat energy out at the condenser, isn't it important that we have a big difference in temperature between the temperature of the refrigerant in the condenser and the outside air? Yes. And if the outside air temperature is really high, is that going to affect how efficiently we get rid of the heat energy?
Yes.
Yeah, it's going to affect it in which way? Negatively or positively? Negative. Right, so we're going to have trouble getting rid of heat energy. And you're going to see this reflected in the pressures that you look at on the AC system when you do that. So we're going to talk about that. HVAC stands for heating, ventilation, and air conditioning. So it's not just AC. It has other functions. We are also using the system to provide heat energy inside the passenger compartment through the heater core. And we're using it to provide some ventilation, some fresh air. And it has some other functions. Besides just removing heat energy from the air, it also must remove moisture from the air. How many of you have AC in your cars right now? A couple of you?
That works.
Yeah, that works. When you have it running and you get out of the car, what do you see dripping down? Water. And that water is water that was removed from the air that was entering the passenger compartment. So we've removed the moisture from the air. Does that have an effect on how you feel? Because what makes you feel cool? What is it that makes us feel cool?
It's dry heat. It's dry, not humid.
No?
Water makes us feel
Does water make you feel cool?
cool. Cold. When you jump in cold water.
Well, when you get out of the water, how do you feel?
Hot.
No, you don't.
Cold. There's the air blowing on the water.
And what's happened?
It's evaporating.
It's evaporating. So without jumping in the pool, how do you feel? What is it that cools us normally? Sweat. Sweat. That's how our bodies cool. We sweat, the moisture from the sweat evaporates, and when it does, it removes a whole bunch of heat energy from our body, that invisible heat that we talked about, latent heat of vaporization, a whole bunch of it. So that's what makes us feel cool. Now, in order for the water to evaporate from our skin, it's evaporating into what? The air. Well, if the air is already full of water because it's very humid, can that evaporation occur easily?
No, that's why you jump in the pool.
That's why you jump in the pool. Because your sweat can't evaporate, so you don't feel cooler as a result. That's why you feel so sticky and hot on those hot, humid days. It's because the air is already saturated with moisture, so it takes long for the moisture from your skin to evaporate, so you feel hot. Remember, you got to have that change of state in order to get the heat transfer effectively. So one of the things our HVAC system does is remove the moisture from the incoming air. And it does that just because as the air is blown across the evaporator, which is cool, relatively cool, the moisture condenses on the surface of the evaporator and hopefully flows out through that drain hole in the HVAC system down to the ground. You guys are going to run into situations where customers are going to be complaining about water dripping on their feet or on the floor on the passenger side because that drain hole is plugged. So that's one of the things you have to do is unplug that drain hole periodically. should be part of your AC service at the beginning of the season. And the other thing that our AC systems do, our HVAC system does, is it removes dust and pollen from the air. Because as that moisture collects on the fins of the evaporator, the dust and pollen in the air collect all the moisture and get carried out and drop down, so they get removed from the air. Now we also, on many of our systems now, we also have cabin filters that we use to additionally remove dust and pollen from the air. So that's a function of the heating and ventilation systems. Has these three subsystems: refrigeration, which is the system that makes up the flow of refrigerant. So that includes the pipes, it includes some kind of a restriction, which I told you could be what? Two items: orifice tube or a thermal expansion valve. This is an older thermal expansion valve. The newer ones are nice, neat little blocks. But something like that, some type of restriction as part of the refrigeration system. And then this piece here, which is in our HVAC module, which is called what? This rectangle.
Evaporator.
No?
Evaporator.
Evaporator, yeah, good. This is the heater core over here. This is the evaporator here. And this is the air inlet into this HVAC system, into this system here, which is one of the subsystems called an air distribution system. We also have in our refrigeration system some type of storage device, or, well, a storage device and a dryer of some sort. Now, in this particular case, this storage device is after the evaporator, so it's on the low side, and it's called an accumulator dryer. An accumulator dryer. It accumulates refrigerant. It allows the liquid refrigerant to collect in the bottom. Then it allows that to evaporate, and it leaves the accumulator dryer as a vapor, hopefully. That way it goes into the compressor. That vaporized refrigerant is then going to get compressed, and when we talk about compressing any medium, what we're really doing is concentrating the heat energy. And that's an important phrase for you to keep in mind, because the function of the compressor is to concentrate the heat energy that we collected from the passenger compartment into the condenser. We want to concentrate it. Now, if we concentrate heat energy, what's that do to temperature? It makes it go up.
So the heat transfer.
So the heat transfer, and that's what, when we get back to one of those concepts of thermodynamics, is that if we can increase the temperature of that refrigerant in the condenser, then it's much easier to get rid of that heat energy to the outside air because of the big difference in temperature. Yes?
So is it true that like warm water will freeze faster?
Yeah,
It is true,
I don't know if that's true.
Because the difference in heat.
because there's energy there to take away.
Does that go by the same law?
Well, the rule is that the bigger the difference in temperature, the faster the heat transfer rate.
So hot water will freeze faster.
Well, I don't know that.
But if you do it at the same
does.
time, hot water does freeze.
I don't know.
It does.
I've never tried.
You've seen Bill Nye?
You got more heat energy to get rid of, too. Don't know the answer.
It's gotta be half.
I've heard that before, but I don't know the answer. So we're concentrating the heat energy into the condenser to raise the temperature. We do that by raising the pressure. As we raise the pressure, what do we do to the vaporization point?
Sooner.
Excuse me, the vaporization condensation point, because they mean the same thing, really. If we raise the temperature, can we change this back to a liquid easier?
Yes.
That's the reason we have pressurized cooling system, right? It's to keep it from evaporating. So the fact that we're raising the pressure and temperature allows it to condense back into the liquid. And when it makes that change in state, it gives off that invisible heat. And the Latin term for that was latent heat. And in this case, it's latent heat of condensation, because you can't feel it. You can't see a temperature change. And then we continue on through our refrigeration loop. This air distribution subsystem is there to distribute air. Yes, sir.
Now, how can you have heat if you can't feel heat?
Well, heat energy is in everything, including an ice cube. If you took an ice cube, it feels cold, but it has heat energy in it. There's no such thing as as cold, really. Everything has heat energy in it. It just has different degrees of heat energy. I shouldn't use that word. It has different amounts of heat energy. Okay. We'll talk more about that concept in a second here. The other subsystem we have that's important to our operation of our system is our cooling system. Before I leave our distribution system, though, notice that we have our evaporator so that every air entering, this is our blower right here, all the air entering into our HVAC system or our HVAC module has to flow by the evaporator. So we're controlling the temperature of the air by doing what? By controlling airflow through the heater core. So when our AC is on, we are keeping this evaporator to the maximum cooling point allowed and possible all the time. And if that's too cold, we increase the temperature by using our temp door or blend door, you'll see it called both, to route some of the air through the heater core to heat it up. So that's how we control the temperature of any of our systems. This is always as cold as we can keep it, which is what, do you suppose?
33 degrees.
Why do you say that, Zach?
Because if anything else, it would freeze.
What would freeze?
The water.
The water that's condensing on the surface, excellent. So we want to keep it as cold as possible, but we don't want that water that's condensing on its surface to freeze, because then it's going to restrict airflow. And if that happens, the customer's going to experience good cooling at first, and then when the water freezes on the evaporator, they're going to lose that. It's going to start blowing warm air, moist air, and they're going to be feeling uncomfortable. The AC isn't quite working right. And then when the water melts off that evaporator, then it will blow cool again. And then it will freeze again. So they'll get that kind of a complaint. It blows cool for a while, and then stops, and blows cool again for a while, and then stops. Here's your clue. You've got something freezing on the evaporator for some reason. And then the air distribution is going to route air to wherever we want it based on our mode position. So the mode doors are going to control where the air comes out the panel ducts, the floor, or the defroster ducts. And then we have our cooling system, which is important to give off that heat energy to the outside air. That consists of the condenser, the radiator, and the fan. The radiator and the fan are both going to affect how much heat energy we can get rid of through the cooling system, subsystem. If we can't get rid of the heat energy, it stays in the refrigerant and causes our high side pressures to start climbing. In extreme cases, it will climb up over 400 degrees and kick off the AC compressor due to high side pressures. So the cooling system plays an important role here in the function of our air conditioning system. Okay, refrigeration system we talked about. Here's the different types of refrigeration systems that we use. So we have a CCOT. CCOT stands for cycling clutch orifice tube. I think this is in your book. You got it? What page?
Page 1-3.
So you can follow along there. Cycling clutch orifice tube. Cycling clutch orifice tube. What does that mean, cycling clutch?
Cycled on and off.
And what we're talking about exactly is this. This is the clutch right here. Our belt is operating this pulley all the time whenever the engine's running, but the AC isn't turning until we apply the air conditioner clutch, which is a magnetic clutch. There's a coil of wire under here, encased in ceramic. When we turn on the AC and conditions are met, we run current through that coil of wire, and quite a bit of current, about 3.5 amps goes through it, building up a magnetic field which draws this dry plate into contact with the pulley. And then we start rotating the compressor itself, the compressor shaft, and in this case, the three pistons, no, R4, excuse me, the 4 pistons arranged around the shaft here. This is called an R4 compressor. You guys have seen these are the earlier ones.
Are those like older than T10 Blazers? Or those with
We were using them on T10s.
Cool.
Not the new Trailblazers.
No, but like the older
Yeah.
Blazer bodies.
Yeah. So, the fact that it's called a cycling clutch orifice tube means we are controlling the amount of refrigerant flowing into the evaporator by turning the clutch on and off. So on this type of system, when it's running, you're going to hear the clutch cycle on and off. Yep, click, and then it'll cycle on, it'll put a load on the engine, and then as the low side pressure starts dropping to a predefined amount, and typically it's around 24 pounds per square inch, then it will cycle off. Now if it didn't cycle off, we'd have too much stuff, too much refrigerant evaporating in the evaporator, and we'd end up with the evaporator freezing up. So we want to maintain enough flow so that we have refrigerant evaporating throughout the whole surface of the evaporator all the time, but not so much flow that it freezes up. We need to be able to stop the flow at some point. Because this thing has a what? To control flow, to limit the flow. An orifice tube which is fixed. It's a fixed hole, fixed orifice. So those things are sized so that it can meet the cooling demand under a variety of operating conditions. So typically they're going to oversize for some conditions, and they may be in fact undersized for some conditions, on high heat load conditions. So they're sized to reach that compromise. And then we have a VDOT system, stands for Variable Displacement Orifice Tube. Now we're going to control the amount of refrigerant flowing through the evaporator, not by cycling the compressor on and off, but by doing what? Changing how much goes in and how much comes out. And we're doing that by varying the displacement. And we use a number of variable displacement type compressors now. This is the V5 compressor, one of the earlier ones. And if I turn this, you can see there's my wobble plate. You can see that plate wobbling right there. That's attached to 5 pistons. Now if I wanted to increase the displacement, I could just change the pressure on either side of those pistons and push this wobble plate back to maximum displacement. Now I can pump more refrigerant. This thing is constantly monitoring low side pressure and varying the displacement so that we get maximum flow through the evaporator without freezing it up. And when it starts to approach that point where it's freezing, as indicated by the pressure, it will move back toward minimum displacement. Constantly controlling flow. We'll talk more about how this works in a minute. So that's variable displacement orifice tube system. Still got a fixed orifice. The next type system you're going to see is a cycling clutch TXV. Cycling clutch tells you again, we're going to cycle the clutch on and off, but instead of using an orifice as our restriction, we're using something called a thermal expansion valve. A thermal expansion valve is going to control the flow of refrigerant into the evaporator based on pressure differences and based on the amount of the temperature of the refrigerant leaving the evaporator. We're going to do both, looking at both, so it can more finely control the amount of flow. Here's our evaporator, guys. We have refrigerant coming in here, and it's evaporating. Ideally, we want it to evaporate. We want that process of evaporation to be occurring around the full surface of this evaporator. Because as it changes state, that's when it absorbs most of the heat. Right? A thermal expansion valve monitors the temperature of the refrigerant coming out. If the temperature, the refrigerant evaporated only to here, and then it moved through as a vapor, it moved through the evaporator as a vapor, it would absorb a little more heat energy. But this absorption of additional heat energy occurred after the change of state. So now instead of getting latent heat of vaporization, we're going to get this thing called superheat. Remember superheat? The definition of which is what? What did I tell you?
When you heat it up after it changes state and after change temperature.
Okay. Any additional heat added after the change of state actually raises the temperature. a thermal expansion valve sees this increase in temperature, and it opens up the valve a little more to allow more refrigerant to flow in to match the heat load, so that we get refrigerant evaporating throughout the full amount, the full range of the evaporator. Does that make sense? The neat thing about it is that it can be so finely controlled that we don't have liquid refrigerant leaving the evaporator. So in a TXV system, whether it be a cycling flush or a variable displacement TXV, we don't need to have an accumulator dryer, because we only have vaporized refrigerant leaving the evaporator, going back to the compressor. We still do need a way to control the, absorb moisture, water, from the refrigerant. So we still need some kind of storage device and some kind of a desiccant. And that is found in the receiver dryer. So, you guys got a place you can write this down? You can write it in your book right at the appropriate section. What I want you to pick up off of this is that on a orifice tube system, we'll have an accumulator dryer, which is what you saw down there. An orifice tube system will have an accumulator dryer. And it's on the low side. The accumulator dryer is on the low side. An orifice tube system will have an accumulator dryer. And it's located on the low side of the refrigeration system. Its function is to remove moisture, and to separate the liquid refrigerant from the vaporized refrigerant. The only thing we want leaving the accumulator dryer is vaporized refrigerant. That's all we want going into this, into the compressor. Remove moisture and separate liquid refrigerant from vaporized refrigerant. So it's a liquid vapor separator. On a TXV system, a receiver dryer is used. Receiver dryer. And the function of the receiver dryer is to remove moisture from the refrigerant and act as a storage device to supply a consistent flow of refrigerant to the TXV. I'll repeat that. The receiver dryer removes moisture from the system, from the refrigerant, so water, and acts as a storage device to provide a consistent flow of refrigerant to the TXV valve. The reason for that is when the TXV senses a superheat condition under a high heat load, it'll open up. But if you don't have a volume of fluid to feed that extra demand, then it'll starve. So you'll end up not getting the effect that you want, which is additional refrigerant flowing into the evaporator. So the TXV, the receiver dryer provides that volume of flow to accommodate the changes in the TXV opening. So our systems are divided into these four types: CCOT, BDOT, CCTXV, and variable displacement TXV. We also further distinguish our systems between the type of refrigerant used, R12 and R134A. R12 we were using right up until 1993 on some vehicles. 94, by 94 everything switched over to R134A. R12, it was determined it was a leading cause of ozone depletion up in the stratosphere. And with that, it increases the UV exposure that we and everyone else is exposed to from the sun, and then all the related diseases and issues that go along with that. So R12 has it's become illegal to manufacture and sell R12. Actually, I shouldn't say sell. You can still buy it. You can afford it, but it's discouraged.
The guy in my shop has like 20 cans and
Yeah.
So,
It's only during like the
$2. Actually, it's
handling that it's bad, right? If it's in the vehicle sealed, it's not a problem. Just
That's correct. The early systems, though, weren't that tight, and when you get an AC system that starts getting around 10 years, they start leaking in joints. So R12 is going to leak if it's not, if the vehicle is not, if components are not replaced on the vehicle. R134A is also going to leak on those systems. So if somebody comes into your vehicle, into your shop for service, and it's an older vehicle with R12, here's the decision they're going to be faced with. I can recharge it with R12, and you can do that even if there's a leak. Oddly enough, very strange. You can't release R12 into the atmosphere as a technician. That's illegal and subject to fine. But if somebody wants to recharge their system, you can recharge it with R12, even if there's a leak. So it's not, you can't tell them it's illegal for you to do that, because it's not, but it's certainly advisable. And of course, R12 is so high in price right now. I think last time I bought it was about $1,000 for a 30-pound container. So they're going to pay so much for it that nobody in their right mind is going to do that. So if somebody comes in with an R12 system, they're going to be faced with making the decision between doing a repair and recharging with R12 or retrofitting to R134A.
Is there any way you can test the system without putting a base in it? Put refrigerant in it?
You can tell if it's been retrofitted by looking at the fittings.
No, I mean like to test to see if it's going to hold.
Oh yeah, for leak chewing? Yes.
Without putting refrigerant in it. Like,
Well, yes and no. Yes and no. The question is, can you test it before you put refrigerant in it to see if it's going to hold refrigerant? And you can. When you evacuate a system, you're drawing a vacuum on it, and then you're going to watch the gauge, and if it goes back up to 0, then you know you've got a leak. It doesn't tell you where the leak is, but you know you have a leak. So then you need to put refrigerant in it to find the leak. Unless it's obvious, of course. And you're going to find the leak using the leak detector or dye, one or the other.
Doesn't most of the new oil have the dye in it?
New oil?
Well, the PAG oil, doesn't that usually have a little bit of dye in it?
Vehicles are coming with the dye in it, but the PAG oil itself doesn't have the dye in it. Well, GM's doesn't. There may be some aftermarket ones that do. But we started putting dye in our vehicles at the factory in 2002.
Maybe that's what it is, the green stuff that comes out.
Yeah.
in all the vehicles? Or just...
Well, initially it was just a few of the vehicles, and it wasn't across the whole line, but now I think it's across the whole line. And I'm not sure of the date. I think it was 2002 when we started doing that, but it was somewhere around there. There should be a label on it saying that there's dye in it, and whenever you guys put dye in it, you're supposed to put a label on saying that you put dye in it. And you don't want to overload it with dye either. CCOT, we talked about it already. Condenser, it consists of these components, the condenser, and this is, all these systems have a condenser. They don't all have an accumulator dryer. If it's a TXV system, it doesn't have an accumulator dryer, it has a receiver dryer. They all have an evaporator. They may or may not have a muffler. A muffler, there's not one shown in this picture, but if you look at an AC system and you see this can sitting there on the AC line, that's a muffler. It's there to dampen out the pressure pulses as the AC compressor is running to reduce the noises. They may have a pressure cycling switch. The CCOT system does, because the compressor does what? It cycles on and off. And it's doing that based on an input from this pressure cycling switch. The pressure cycling switch is in the low side. It's in the low side. because we want to monitor the pressure of the low side so that we can keep the evaporator from freezing. There is a pressure-temperature relationship between refrigerant, and if you look on, I think it's in this book, maybe not. Take a look on page 2-13 in your books, please. You have two tables there, one for R12 and one for R134A. If you look at the one for R134A and you look at the evaporator range, notice that at about 24 pounds per square inch, the temperature of the refrigerant is around 28 degrees. The surface of the evaporator is going to be about 5 to 10 degrees higher than that. So most of our systems that use a cycling clutch system will cycle off as low side pressure starts getting to around 24 pounds per square inch. That will keep our evaporator from freezing. So that's what you should be seeing. And then when the compressor shuts off, what's going to happen to the pressure in our refrigeration system? It's going to equalize. It's going to drop on the high side, increase on the low side. It's going to equalize. And when the low side pressure starts getting up to around 40 pounds per square inch on an R134A system, the compressor cycles back on again to run it again. So we're constantly cycling it on and off to maintain maximum flow of refrigerant, maximum evaporation in the evaporator without the moisture freezing on the surface. So that pressure-temperature relationship is important to keep in mind for a couple of reasons. If you take a look at that same chart and you look at the temperature of the refrigerant at 60 degrees, 65 degrees, can you see it at 65 degrees Fahrenheit? The pressure is around 64 pounds per square inch. If you have a tank of refrigerant that has been sitting outside the sun, for a few hours in a shady area, I think it's 12 hours typically, so that it is at ambient temperature, that's the point here, and you hook a pressure gauge up to it, it should match this pressure relationship table for R134A. So it should be right around the 64 degrees plus or minus 10%. If it's greater than that, that means that the refrigerant is not pure. It's contaminated with something. Typically non-condensables, which is air. Air is a non-condensable. So that's useful for you. If you had a vehicle come in that had a poor AC performance concern and it's set in your bay overnight, because it has to be at ambient temperature in order for the test to be valid, and you hook your pressure gauges up to it, your ACIntro5, your static pressure should match this table. Now, if the vehicle's been run, then it's not going to match because it's been heated up. But if it's been sitting overnight, then it should match this table, and if it doesn't, that means there's probably some non-condensables or air in that system. So what do you do about that? You recover the refrigerant. Unless your machine senses some other contaminant, then it won't recover. But if it's just air, you're going to recover the refrigerant, and the ACIntro5 is going to separate the air from the refrigerant as it recycles it. Yes, sir?
So what do you do if it's contaminated, if the machine
If it's contaminated, you're not going to recover it. Here's what some dealerships or some businesses will do. They'll have a separate machine for recovering contaminated refrigerant. Now, they sell machines for that. They're called scavengers. You recover the contaminated refrigerant, it gets stored in a separate container until it's full, and then you have to pay somebody to come and take care of it as hazardous waste. I know some garages are using their ACR4 for that. But you really don't need the ACR4 anymore with the ACR2000. Although I also know some garages are using both. They use the ACR4 as a backup to the ACR2000. You can do that if it's non-warranty work. If it's warranty work, you've got to use the ACR2000 because you have some codes that you have to record on the repair order. So, pressure cycling switch. Some will have a thermostatic switch to prevent, it just is an additional control to prevent icing at the evaporator. Thermostatic switch may be a switch that's directly, on older systems, that was directly connected into the AC, to the compressor control circuit. Or nowadays, it's a thermistor that is an input to the ECM or PCM, and the PCM watches that, and when the evaporator temperature starts getting to the point where the moisture is going to freeze on the surface, it shuts off the compressor. So some will use that. They all have some kind of pressure cutoff switch, high pressure cutoff switch, and a low pressure cutoff switch. The low pressure cutoff switch shut off the AC system if the pressure starts getting too low. Now, this is on the high side quite often, but if the high side pressure starts getting too low, it's going to shut it off so that we don't burn up our compressor. Because again, we're relying on that recirculating refrigerant and the oil that it's carrying with it to lubricate the compressor. The high pressure cutoff switch is going to cut off the AC if high side pressure starts getting too high. That's a requirement by law, so that we don't blow off refrigerant into the atmosphere. Because it's illegal to release R134A into the atmosphere too. Even though it's more environmentally friendly than R12, it ain't perfect. Some systems utilize a pressure sensor as an input to the PCM. Most of our systems are using something like this now, which is kind of cool because now you can just hook the Tech 2 up and watch your high side pressure. You can actually get pressure readings on it. We don't typically have a low side pressure sensor on most of our systems, but you can at least look at high side without hooking the ACR 2000 up there. VDOT, big difference is that the compressor is not a cycling clutch. This, oh shoot, where's that VDOT there? There's a VDOT. It does still have a drive plate, and it still has a clutch. So it can still be engaged and disengaged. So when you don't have the AC on, it's going to be disengaged. When you turn on the AC, if conditions are right, we will engage it. But it doesn't cycle on and off. We're going to vary the flow by varying the displacement, the angle of that waffle plate.
How does it do that? By pressure on the plate?
Yeah, I'm going to talk about how that works a little later. It may have a muffler. They all, again, there's some kind of pressure cutoff switches there, and in some cases a pressure sensor. Cycling clutch TXV, the big difference here, has a receiver dryer instead of an accumulator dryer. May have a muffler, may still have a thermostatic switch, pressure cutoff switch is still there, may have a pressure sensor, but it has a TXV valve as opposed to an orifice tube. A TXV valve as opposed to an orifice tube. And VDTXV, same thing. Has a receiver dryer, a TXV instead of an orifice tube, and the clutch doesn't cycle on and off. Vary the displacement. So, how do we tell the difference between a cycling clutch orifice tube system and a cycling clutch TXV? By looking at it.
Look for a receiver dryer.
Accumulator dryer.
Good. Okay. So you're all right. You can look for a TXV valve, and you can recognize a TXV valve because where the lines go into the evaporator, you're going to see an aluminum block. That's the TXV valve. It doesn't look like this anymore. It used to look like this. Or you can look to see if there's a receiver dryer or an accumulator dryer. Now, how do you know which is which?
One's on the high side, one's on the low side.
Excellent. Receiver dryer is on the high side. You got liquid refrigerant flowing into it and liquid refrigerant flowing out of it. Always. If it's an accumulator dryer, you have a combination of vapor and liquid refrigerant flowing into it and vapor flowing out of it, hopefully. And it's on the low side. It's after the evaporation.